July 17, 1981. A Friday evening in Kansas City, Missouri. The brand new Hyatt Regency Hotel is hosting its weekly tea dance in the atrium lobby. Over 1,600 people are packed into the space, dancing, drinking, socializing. Above them, two suspended concrete walkways span the width of the atrium, connecting the second and fourth floors. Dozens of spectators are standing on both walkways, watching the dancers below. The band is playing. The crowd is moving. And then, at 7:05 p.m., a sound like a thunderclap echoes through the atrium. The fourth-floor walkway tears free from its support rods. It crashes onto the second-floor walkway directly below. The combined weight of both walkways, approximately 2,000 tons of concrete and steel, slams onto the crowded dance floor. 114 people are killed. Over 200 are injured. It is the deadliest structural failure in American history. And it happened because of a design change so simple it could be sketched on a napkin. The Hyatt Regency Kansas City opened on July 1, 1980, after years of troubled construction. The hotel was designed to be a showpiece. Its centerpiece was a spectacular multi-story atrium lobby, inspired by the grand hotel atriums that were becoming fashionable in American architecture. 3 suspended walkways crossed the atrium at the second, third, and fourth floor levels, connecting the hotel wings on either side. The walkways were designed to hang from the ceiling by steel hanger rods. In the original engineering design, each walkway was supported by a set of long steel rods that ran continuously from the ceiling all the way down through both the fourth floor and second floor walkways. Picture it like a thread running through 2 buttons. A single rod passes through both walkways, with a nut at each walkway level to hold them in place. The load from both walkways is transferred directly to the ceiling through these continuous rods. Each connection point only bears the weight of one walkway. This design was structurally sound. It had been calculated, reviewed, and approved. If it had been built as designed, the walkways would have held. But it was not built as designed. During construction, the steel fabricator, Haven Steel Company, contacted the engineering firm, GCE International, with a concern. The continuous rod design was difficult to build. Threading a long rod through the fourth floor walkway's box beam, then continuing it down to the second floor walkway below, was complex and time-consuming. They proposed a simpler alternative. Instead of one continuous rod, use 2 shorter rods. The upper rod would run from the ceiling to the fourth floor walkway. A separate, second rod would hang from the fourth floor walkway down to the second floor walkway. On paper, this seems like a minor fabrication detail. The walkways still hang. The rods still connect to the ceiling. Everything looks the same from the outside. But from an engineering perspective, this change is catastrophic. Here is why. In the original design, each hanger rod connection at the fourth floor walkway only supports the weight of the fourth floor walkway itself. The second floor walkway hangs independently on the same rod, with its weight transferred directly to the ceiling. But in the revised design, the fourth floor walkway connection must now support both its own weight and the entire weight of the second floor walkway hanging below it. The load on that single connection point has effectively doubled. The box beam connection at the fourth floor walkway was never designed to carry that doubled load. It was a simple welded steel channel with the rod passing through it. Under the original design, it only needed to hold the fourth floor walkway. Under the revised design, it needed to hold both. Nobody recalculated the connection to verify it could handle the additional load. The change was communicated between the fabricator and the engineering firm through a series of phone calls. There is no evidence that the engineering team ever performed a formal structural analysis of the revised design. The engineer of record, Jack D. Gillum, and his project engineer, Daniel M. Duncan, approved the change. Years later, both would dispute who actually reviewed and approved it, each pointing to the other. But here is the detail that makes this case a landmark in engineering ethics. Even the original design was barely adequate. Later analysis showed that the original continuous rod connection only met about 60% of the Kansas City building code requirements for that type of load. It was already undersized. The revised two-rod design reduced the capacity even further, to roughly 30% of code requirements. The connection that was actually built could hold less than a third of what the building code demanded. The hotel opened in July 1980 with the flawed walkways in place. For over a year, thousands of people walked across them daily. The connections held, but just barely. They were carrying static loads, the weight of the walkways themselves plus occasional pedestrians. The safety margin was almost non-existent, but the walkways did not fall. Then came July 17, 1981. The weekly tea dance attracted an unusually large crowd. Over 1,600 people filled the atrium. The dance floor was packed. And dozens of spectators crowded onto the second and fourth floor walkways to watch. They were standing, moving, swaying to the music. This dynamic loading, the rhythmic movement of dozens of people on the walkways, added stress that the connections could not withstand. At 7:05 p.m., the hanger rod connections on the fourth floor walkway failed. Witnesses described hearing a sharp crack, then a deep groaning sound as the steel began to tear. The fourth floor walkway dropped, slamming into the second floor walkway below it. For a fraction of a second, the second floor connections tried to hold the combined weight of both walkways plus all the people on them. They could not. Both walkways plunged to the ground floor, crashing onto the dancers below. The scene was catastrophic. 2,000 tons of concrete and steel had fallen onto a crowd of people. Many were killed instantly, crushed beneath the walkways. Others were trapped, pinned under debris with injuries so severe that rescue workers later described the scene as resembling a war zone. The atrium floor, which covered an underground parking area, partially collapsed under the impact, creating additional hazards. Emergency responders from across Kansas City converged on the hotel. Doctors and nurses from nearby hospitals came on their own, some still in street clothes. Off-duty firefighters and police officers arrived to help. The rescue operation continued through the night. Structural engineers had to be called in to determine whether the remaining third-floor walkway, which hung from a separate set of connections, was safe. It was evacuated as a precaution. The final toll was devastating. 114 people killed. Over 216 injured. Many survivors suffered permanent disabilities. It remains the deadliest structural collapse in American history, a record it has held for over 4 decades. The investigation was led by the National Bureau of Standards, now known as NIST. Their findings were unambiguous. The walkway collapse was caused by the change from a 1-rod to a 2-rod hanger design, which doubled the load on the fourth-floor box beam connections. These connections were never designed for that load, and the change was never properly analyzed or recalculated by the engineering team. The professional consequences were severe. In November 1985, Jack D. Gillum and Daniel M. Duncan had their professional engineering licenses revoked by the state of Missouri. Gillum's firm, GCE International, lost its certificate of authority. It was one of the first times in American history that licensed engineers were held professionally accountable for a structural failure of this magnitude. Criminal charges were considered but ultimately not filed, a decision that remains controversial to this day. The Hyatt Regency disaster transformed the engineering profession in the United States. It became the most studied case in engineering ethics courses and is still taught in virtually every civil and structural engineering program in the country. The case established critical precedents about the responsibility of the engineer of record. When a fabricator proposes a design change, the engineer must formally analyze that change and verify it meets code requirements. A phone call is not enough. An assumption is not enough. The math must be done. The case also raised painful questions about communication failures. The fabricator proposed the change because the original design was difficult to build. The engineers approved it without performing calculations. Nobody involved was trying to cut costs or commit fraud. There was no corrupt CEO, no bribed official, no deliberate negligence. It was simply a case where a seemingly minor change fell through the cracks of a complex construction process, and nobody caught it. That is what makes the Hyatt Regency collapse so haunting. It was not caused by greed or corruption. It was caused by an assumption. Someone assumed the change was minor. Someone assumed someone else had checked the numbers. Someone assumed that if it looked the same, it must work the same. And 114 people paid for those assumptions with their lives. The math that could have prevented this disaster would have taken an engineer less than an hour to complete. A simple calculation of the load on the box beam connection under the revised design would have immediately shown that it was inadequate. That 1 hour of work, never performed, is the difference between a standing building and 114 coffins. Today, a memorial stands near the site in Kansas City. The Hyatt Regency Hotel was renovated and eventually rebranded. The walkways were never rebuilt. And in engineering schools around the world, professors use this case to teach a lesson that every engineer must learn before they are trusted with human lives. When someone proposes a change, no matter how small it looks, you check the math. Because in structural engineering, assumptions do not hold up buildings. Calculations do.